Hello, my name is Toshiki Kurita. I'm a postdoc at the Max Planck Institute for Astrophysics. In this talk, I'd like to talk about the probing the primordial parity violation with the late-time universe observables, especially intrinsic galaxy shapes and dark matter halo shapes. This is the outline of my talk. The first, I will briefly explain our motivation for why we consider galaxy shapes and describe how its statistics are sensitive to the parity violation in principle. And next, I will introduce the cosmological correlation of galaxy or halo shapes, the so-called intrinsic alignment, reviewing the observational measurements and the physical model and a physical picture of intrinsic alignment as a tensorial bias tracer of the underlying matter field. Then I will present our recent work on searching for the parity violation with galaxy shapes as an example. So this work is motivated by some inflationary models that predict the generation of parity violating signals in the early universe. In particular, in the latter part of my talk, I will focus on the scalar type parity violation, which is characterized by the trispectrum of the curvature perturbation. The trispectrum here can be decomposed into the parity even and parity odd parts with respect to the sign under the parity transformation. So our target is this parity odd component, or equivalently, the pure imaginary part of the trispectrum. And the CMB and large-scale structure would contain the signature of the parity violating signal. In the case of the galaxy clustering, we need at least 4-point statistics of galaxy density field to probe the underlying parity violation, because the density field is the scalar field in the three-dimensional space. So if you have two galaxies and the mirrored configurations can be reproduced by the three-dimensional rotation of the original configurations. And same is true for the 3-point statistics. So in this sense, the 2 or 3-point statistics are not sensitive to the parity violation under the statistical isotropy. But if we have the 4 points of galaxies form tetrahedron, and we can show that there are some configuration not overlapping with the mirrored configuration by the 3-dimensional rotation. So some recent 4-point correlation function analysis reported the evidence of detection of the parity violating signal, but we still do not fully understand whether the signal is physical origin or the systematics. So it would be beneficial to have an additional independent probe to investigate the parity violation based on the late-time universe observables. So here we consider the galaxy shapes. So if you imagine two galaxies, but with additional information on shapes. So here, not just 2 points, but the 2 extended sources. So then we can show that some mirrored configuration cannot be reproduced by the 3-dimensional rotation of original image due to their tensorial structure at the endpoints. This means that the shapes are sensitive to the parity at the level of 2-point statistics. So this is our main motivation. to study the galaxy shapes. So here I'd like to introduce the intrinsic alignments. So intrinsic alignment is the correlation of shapes with the surrounding large-scale structure. And this is not the weak lensing effect, as I will describe later. And here we are considering the very large-scale correlations or cosmological correlations at about 100 megaparsec scales, which is well beyond the scales of typical halo formation or baryonic effects. So if there is a non-zero correlation between such distant galaxy shapes, then the signal should originate from the underlying gravitational or primordial perturbation. And there is an increasing interest in intrinsic alignments as a new cosmological probe, such as an isotropic primordial non-Gaussianity, growth rate, BAO, and a stochastic gravitational wave backgrounds. So the intrinsic alignment signals have been detected with various observational data for RA type or elliptical galaxies, but not yet for star-forming or spiral disk galaxies. And right panel shows the measurement of the IA signal, the galaxy shape, and galaxy density cross correlation. So x-axis is the separation between the two galaxies, and y-axis is corresponding to the radial distortion or ellipticity towards the other galaxy position in a pair. And the null signal corresponds to the random orientations. And we can clearly see the non-zero signal and it's non-vanishing even at 10 or 100 megaparsec separations. And the scale dependence of large-scale signal is in good agreement with the linear theory of intrinsic alignment, the so-called linear alignment model, which also I will describe later. So for the direct measurement of intrinsic alignment, basically we need both imaging and spectroscopic dataset. And spectroscopic survey, we obtain three fundamental observables, two angular coordinates, theta and phi, and the spectroscopic redshift, the spec here. And assuming a fiducial cosmology, we convert them into the moving distances, x, y, and z. So we now have the spatially three-dimensional distribution of galaxies. On the other hand, we can obtain precisely measured ellipticities, gamma 1 and gamma 2, for each galaxy from the imaging survey. So if we consider the combination of these two galaxy surveys by assigning the observed ellipticities to the position where the galaxy is located, then we can now construct the spatially three-dimensional two ellipticity fields, the gamma 1x and gamma 2x, in addition to the standard galaxy density field, delta x. And in Fourier space, these two degrees of freedom correspond to the E and B modes. And then we can measure the power spectrum of the intrinsic alignment, such as the E mode galaxy cross power spectrum, and also the E mode, B mode power spectrum, which is considered to be parity sensitive signal. So here is an example of the actual measurements in Fourier space, the intrinsic alignment power spectrum from the SDSS both galaxies. The blue data points for the E mode density cross power spectrum, and the orange is for the B mode density cross power spectrum. And there again, the clear detections. So we can measure the intrinsic alignment signal using a combination of spectroscopic and imaging surveys. I'd also like to briefly mention the difference between weak lensing and intrinsic alignment, since IA is the mostly discussed as a contamination in weak lensing studies. The observed shape contains both the weak lensing distortion and intrinsic alignment distortion component, but the physical origins are quite different as shown in the right figure. So the IA signal is sourced by the surrounding large-scale structure, but on the other hand, the weak lensing signal is sourced by the foreground large-scale structure. And if we take the correlation of the observed galaxy shapes, then the IA-related terms appear in addition to the pure weak lensing signal. And since the IA signal partly mimics the weak lensing signal, it needs to be precisely modeled to obtain an unbiased result from the weak lensing analysis. But our signal here is gamma IA, so intrinsic alignment itself. So the question is, what physically aligns intrinsic galaxy shapes? The simplest answer would be the tidal field. And before going to the physical model of intrinsic alignment, I would like to first define the shape of objects. And we always approximate a galaxy or dark matter halo shape as a triaxial ellipsoid by using the inertia tensor defined by this equation. So this is a second moment of the density profile or luminosity profile. So this is a symmetric rank 2 tensor. So there are 6 degrees of freedom. One is for trace part, and the other 5 are for the trace-free part. 2 are distortions, 3 are for the orientation of object. And in this talk, I will only focus on the trace-free part because the trace part or size of object is a scalar field in the 3-dimensional space as the standard galaxy density field. So we only consider trace-free part. And if we have the inertia tensor for each object, galaxy or dark matter halo, then we can construct a 3-dimensional shape field. And in this talk, I will denote the shape field as the Sij X. And we are interested in the statistics of the shape field, especially the power spectrum defined by this equation. The power spectrum here has many indices and complicated structure due to the tensorial structure of the shape field. But there is an efficient mathematical decomposition, the so-called helicity decomposition or SVT decomposition for the traceless tensor field. So by performing the projection on those helicity bases, we can isolate the independent components in the power spectrum. And now the previous 5 degrees of freedom in the trace-free part in real space correspond to the 5 independent polarization states in Fourier space. So one scalar, one longitudinal scalar, 2 vector, and 2 tensor modes. Or in other words, 1 helicity 0, 2 helicity 1, and 2 helicity 2 modes. And in terms of the parity, we have 3 parity even and 2 parity odd components. And these odd components correspond to the difference between the power spectrum of right-handed and left-handed modes for each helicity. So again, the shapes are sensitive to the parity violation at the level of 2-point statistics, and they are two independent components. And here, let me introduce the physical model of intrinsic alignment, linear theory called linear alignment model. A linear alignment model is defined by this equation. So the shape of object is statistically proportional to the large-scale tidal field at the same point x with the constant bias coefficient. And this linear relation is analogous to the linear bias relation of the galaxy clustering. So galaxy density field is proportional to the underlying matter field at the linear scales. And right panel shows the linear alignment predictions. So if you pick up the one Fourier mode of the underlying large-scale matter density field, then the corresponding tidal field Kij can be described by these blue arrows. And then the linear alignment model predicts that the shape of galaxies here statistically slightly compressed in this direction. On the other hand, here shape is should be slightly elongated in this direction, and so on. So this spatial pattern of shapes is predicted by a linear alignment model. And in Fourier space, this pattern is exactly corresponding to the longitudinal scalar mode or helicity zero mode. That means linear alignment model only produces the helicity zero or parity even mode. So if we want to probe the underlying parity violation with intrinsic galaxy shapes, we have to use the higher order terms. So in our recent work, we first compute the parity-odd component of the intrinsic alignment power spectrum using perturbation theory, and then compare the perturbation theory result with the n-body simulation. So the shape field can be expanded perturbatively in analogous to the bias expansion of galaxy density field. And at linear order, we have the linear alignment term. And also at the second order, we have basically 4 terms: the nonlinear evolution of matter, and advection, tidal torquing, and density weight. And similarly, we have the third order term, Sij3. And using this perturbative expansion, we can compute the intrinsic alignment power spectrum up to the order of the delta to the fourth. So we have the linear alignment model and also the P22 type and P13 type terms. And after the projection onto the helicity basis, we can extract the parity-odd component. And the parity-odd component can be represented by this complicated equation. But the structure is that the integrals, or two loop integrals of the product of the gravitational corners and the input parity odd trispectrum. And this parity odd trispectrum is a model dependent. So once we assume a parity violating physics, then we can compute the perturbation theory prediction using this equation. And this integral can be represented by this diagram. And we can show that the contribution of this integral is dominated by the so-called collapse limit of the input trispectrum. And collapse limit is the soft limit of the one of the diagonal of the tetrahedron. So we naively expect that the intrinsic alignment power spectrum becomes very large if the input parity-odd spectrum has a very large amplitude in the collapse limit. So in this work, we consider the following two trispectrum templates as working examples. The first one is squeeze type model defined by this trispectrum. And second one is a collapse type model defined by this trispectrum. And squeeze type model has a trispectrum has a very large amplitude in the squeezed limit, where the one of the side lengths of the tetrahedron is very small. On the other hand, the collapse type trispectrum has a very large amplitude in the collapse limit. And in particular, the second one, the collapse type model, is physically motivated by the so-called U1 gauge model. So this is one of the main results of our work. So the bottom panel shows the perturbation theory calculation in the case of the squeeze type trispectrum, the blue line, and in the case of the collapse type trispectrum, the orange color. And we can clearly see that the intrinsic alignment power spectrum is more sensitive to the collapse type model as we expected. And also there is a scale-dependent enhancement with the collapse type model in the K0 limit, which can be explained by stochastic contribution. And noting this parity-odd power spectrum, the three-dimensional version of EB power spectrum. So now we have a perturbation theory results. So compare them with n-body simulation results. So basically, we modify the public initial condition generator by adding the non-Gaussian correction to the usual Gaussian initial condition, so that the trispectrum of total non-Gaussian potential realizes the previous two model templates. And with the modified initial conditions, we run the n-body simulation with gadget 4 and identify the dark matter halos with FOF algorithm and measure the shape tensor for each halo using the member particle positions, then measure the helicity power spectrum using the standard power spectrum estimator with the projection onto the helicity basis. So this is a result in the case of squeeze type initial condition. So left panel shows the parity-odd component of helicity 1, and right panel shows a helicity 2. And black points for the measurement in the Gaussian initial condition as a reference, and blue and red points correspond to the case of the parity violating initial condition. And there is, in this squeeze type parity violating trispectrum, there is no clear detection. So the power spectrum of intrinsic alignment is not sensitive to this model. On the other hand, in the case of collapse type initial condition, there is a very clear detection, and also there is a strong scale-dependent enhancement in the K0 limit, which is in good agreement with the perturbation theory prediction, the solid curves. So the scale-dependent enhancement can be explained by a stochastic contribution. The collapse limit of the trispectrum corresponds to the large-scale correlation of the small-scale variances in real space. And this is non-deterministic correlation. So that's why we call this as stochastic contribution. And this stochastic correlation is known in the case of tau NL cosmology. But in this case, the intrinsic alignment responds to the large-scale correlation of the quadrupole of the small-scale local power spectrum. And also, theory side, the perturbation theory prediction is cutoff dependent. So it has to be normalized by adding new operator, a stochastic bias operator, which reproduces the scale-dependent enhancement. So let me conclude my talk. So intrinsic alignment can be a new proof of the primordial parity violation in cosmology. In particular, the power spectrum proves the collapse type scalar parity violation. And it would be complementary to the 4-point correlation function analysis of galaxy density field because that signal is more sensitive to the equilateral shape of the trispectrum. And also, there would be less systematics in the covariance estimation at large scale because it is the power spectrum and should be the covariance should be dominated by standard Gaussian and Poissonian shaped noise term. So future works, we can do the analysis with actual data set by combining the imaging surveys and spectroscopic surveys. And also we can go to the higher order statistics, such as 3-point correlation function and bispectrum intrinsic alignment. And also it is interesting to investigate the other parity violation, such as a tensor force effect to the intrinsic alignment shape. That is, thank you very much.